This is my first time at the Midlands Azure User Group. So for those that don't know me, I'm Liam, and I'm an engineer, or newly renamed as an architect at Microsoft. I sit in the app innovation team, and a big part of my role is working with customers in that kind of intersection between adopting the cloud, moving into cloud native, and bringing developers on that journey and helping developers be more productive and gain more traction as they start adopting these services. And there's this really interesting area of, well, I think is really interesting, hopefully you will towards the end of the session as well, around Kubernetes that not many people know about. And it's the API. And we quite often refer to the Kubernetes API server, but we don't often talk about the API and how we can actually use the API as developers to do some pretty powerful stuff. For those that perhaps aren't quite familiar with the inner workings of Kubernetes, I'll give you the 30-second whistle-stop tour. It's split up into two main areas. We've got the control plane on the left-hand side. This is the bit that we don't usually care about. And we've got the bit on the right-hand side, the agent pools, or often referred to as the data plane. This is where our stuff happens. When we're running workloads in Kubernetes, it's running over here on the right-hand side. And there's this little component. And whenever we draw Kubernetes, we always draw it as this really small box in the middle that we call the API server. But actually, it's the most fundamental part of the cluster. It's the front door into the Kubernetes cluster, whether we are talking to the cluster or whether the components inside the cluster are talking to one another, everything goes through the API server. The documentation talks about the API server, and it says it lets users, different parts of your cluster, and external components communicate with one another. And the bit that we're going to be focusing on today is the external components and how we as developers can build these external components to leverage the inner workings of that API server, like the scheduler, like the controller manager. So a couple of use cases where we've seen companies and people doing this in the past. The first one is a Kubernetes operator. We can think of an operator as a component that sits inside the cluster that automates you and me. When we see something that goes wrong inside the cluster, we might jump onto it, run some commands, restart something. We can build an operator to automate that process. Client tooling, hands up if you've installed a tool called kubectl or kubectl, maybe some people might refer to it as. Client tooling. These are the remote controls for Kubernetes. We sit there on our local machine, we type in some commands, something happens in the background. And we can build our own client tooling to interface in with that API. And then finally, a project that I worked on relatively recently is high performance compute, where we want to dispatch work into a Kubernetes cluster across thousands or millions of cores and have this calculation happen in parallel across really discrete specialized hardware. And we don't want to have to write the code to orchestrate and manage all of that ourselves. Why not let a specialized piece of kit like Kubernetes do that for us? So a bit of an intro on the API. It's HTTP based. It also has a gRPC interface, but most of our clients and most of our SDK tooling uses the HTTP API. We think of it as the front end for the Kubernetes control plane, and it's the interface that we use to interface with, interact with, and query objects that live inside the state engine. Supports both JSON and the protobuf protocol. Typically, again, we're going to lean onto the JSON side of this, so it's an API and it's an interface that we're familiar with. Thankfully, we don't have to worry about YAML and getting those indentations right. And then finally, resources in the API are declarative. And this is unlike most HTTP APIs that we talk to. Normally, when we send a request to an API saying, hey, create a user for me, and it returns back saying successful, that implies that there is a user sat in a database somewhere and the transaction has completed. In Kubernetes, all it means is the state has been stored. So if we create a pod, if we create a container inside Kubernetes using the API, it doesn't necessarily mean that it's running. It just means the state has been stored. And we'll see an example of this in a little minute. We don't like talking to APIs directly. There are client libraries available across all common languages. I was surprised to see Haskell on this list. Hands up if you've heard of Haskell before. Hands up if you've written Haskell before. Yeah. But yeah, apparently there is a client library for Haskell to interface with the API server. You'll note that the URL there for the Go client library is slightly different to the rest. And this is because the Go library is maintained by the core Kubernetes team. It's the one that they use internally within the Kubernetes components, whereas the rest are typically used for external components. It's worth mentioning, we all love auto-generated client libraries. All of these libraries are generated based on the Open API definition, which means that as we switch from one client library to the next, they're all pretty similar. The way that we interface with them, the object names, etc., are all pretty similar. So before we dive into a demo, there's a couple of fundamentals that I want to introduce first. The first is authentication. Now, when the Kubernetes project first launched, the way that we authenticated with the API was basic authentication. We would give a username and password, and we would send it in plain text in the HTTP request. No surprises. As Kubernetes grew, that didn't last very long. There's now 101 different ways that we can authenticate with Kubernetes, but we can't access any of them through the client tooling. The authentication has to be done ahead of time and exposed to the client readily before the application starts running. So this is something we have to be aware of. We need to do that authentication piece before we run the application. There's two options available. On the left, we've got kubeconfig. This is a file that exists on disk somewhere in the cluster on the machine. And in here, there'll be a client ID and a secret, or the path to an executable that is capable of generating that secret. And we can see a couple of programming languages there. Python, as always, the most straightforward. Config.load config file. The other way of doing this is inside a cluster. So if we are running our application inside the Kubernetes cluster, we can actually access the service account of the cluster or of the pod and authenticate directly with that API. So on the right-hand side here, we've got load in cluster config. It's worth mentioning that the one on the left will fall back to the one on the right, assuming it's not available. So if we want an application that's going to work both in and out of a Kubernetes cluster, we can just do that one on the left and get us where we need to go. It's also worth exploring a little bit about the Kubernetes API. Firstly, some of the objects in that API are namespaced. So within the API control plane, we have this concept of a namespace. This is a logical grouping of objects inside the cluster. And some objects, like a pod, are grouped by this namespace, whereas others aren't. And we need to know the difference when we're looking at making a request to say, hey, list pods, go and retrieve a list of all the pods running in the cluster, versus go and list all of the cluster role bindings. We need to know whether that resource is namespaced or not. Once we've figured that piece out, we need to know which API group that object exists within. So internally within the Kubernetes project, different parts of the API are managed by different teams and different subdivisions of the project. And they all have their own API group. We have the core group, we have the applications group, we have the batch group, and all of them are responsible for their own maintenance. And we need to know which API group, the object that we want to interface with, where it lives. So for example here, the first example is creating a deployment. This exists within the version 1 of the application group. The second one here is creating a job, and this is in version 1 of the batch group. And we need to know these groups and these conventions to be able to access those objects. So we'll dive into a quick demo just to see some of this in action. If I don't fall off the side of the table here, we'll give it a go. So we're going to look at two examples here. Both of these are .NET Console applications, and I will zoom that font in just a little bit. The first is going to be the equivalent of our client tool, and it's going to go to the cluster and say, hey, just list all of the pods that are running inside this cluster. This is something that we could do with kubectl. This is something we can do with the Kubernetes dashboard. But just to kind of help illustrate some of the things that we've got to do to interface in with the cluster. So first of all, we've got a console application here. If I look at our dependencies and look at packages, you'll see that I've installed the Kubernetes client NuGet package into this project. And this is going to give me access to the Kubernetes namespace within the .NET library. From there, and we'll just hide that there so we can see more of the code, we're first of all going to load that configuration in. And we can see here that I'm using the build default configuration. This is going to pull the authentication context out of that kubeconfig file that happens to live on my C drive somewhere. I'm then going to instantiate a Kubernetes client. This is a lightweight HTTP proxy. Usually in .NET applications, we instantiate these as singletons and let the HTTP client pool manage all of the connections out to the API. We can then see I'm using that client and I'm accessing the core v1 API group to say, hey, can you list all of the namespaced pods for me? So this is, again, those two things that we need to know. We need to know which API group we're in, and we need to know whether the object we're talking to is namespaced or not. And in this case, a pod happens to be namespaced. Once we've got the results down, we're going to just iterate over that and output that into the console. And we can have a look at this particular application running. We can go and run .NET run list pods. It's going to think about it. And I happen to have 3 pods running inside this cluster. So for those of you that have worked with kubectl or Kubernetes before, you'll be familiar that you could also run kubectl get pods using the official client library to get the same output. This is an unlikely scenario. As developers, we're not likely going to use the client tools to create our own CLI. We're going to use kubectl, right? But it's just to kind of illustrate, it's that hello world example of how do we take that client library and interface with it using .NET. The next example that I wanted to quickly show is the creation of an object. So we can see here the same stuff at the top there. We're creating that configuration context. We're creating the Kubernetes client. And we're then going to define a new object. So I'm going to define the specification here for a pod. Again, grouping is important. Everything inside the Kubernetes API is versioned. So we can see here that we're creating a version 1 pod. We're going to call it demo pod, and we're going to run the latest version of Nginx inside this pod. And as we come a little bit further down here, we can see that I'm going to use the core 1 group, and I'm going to create a namespaced pod. Now, just to reiterate, this is a declarative API. So when this returns back and says HTTP 200 success, all that means is that the request to create a pod has been received. And in the background, Kubernetes is then going to pick up that request, and eventually, within a given time, the pod will be up and running. Sorry?
Why 200, not 200? 200 was accepted.
It will be in the 200 group, so it will probably be a 201.
That was accepted. Fine.
I'll check, but I think it will be a 200 because it has been committed to the database, but I will check. So we can go ahead and run this. Let's just grab that command to save me typing it out. We'll run that project create pod. It's going to confirm on the left-hand side that that pod has been created. On the right, we'll go back to that kubectl tool, and we can see, in this case, demo pod is running, and it's been running for 6 seconds. We'll continue that just to delete that pod and just check that it has disappeared. Now, again, not a likely scenario for what we would use the API server for, but it does start sparking a little bit of interest on, actually, I can programmatically at runtime deploy workloads into my cluster. Usually when we think about Kubernetes, we think about having a GitHub Actions workflow or an Azure pipeline or similar, doing a kubectl apply and deploying a workload into my cluster and having it as this static runtime, a collection of pods that are running inside the cluster. But actually, when we think about the fact that we can programmatically handle some of this stuff, we can start thinking of scenarios where we would want to dynamically create pods, workloads inside the cluster after deployment time. Yes?
Can you give a use case where we have to create a pod using programming instead of, auto scaling that up?
Yes. Can I give you one in the next demo? Yeah? If I don't answer the question, come back to me. But why? It's a part of the question here. So why not do it at deployment time? Or why shouldn't we just talk to an API? Why should we go through the Kubernetes control plane? And the short answer is that we can leverage the Kubernetes scheduler. There's a very powerful component inside Kubernetes called the scheduler. And this component is there to figure out the best place for us to execute a program, a container. So we could have lots of discrete types of calculations, processes that we want to run. Some that require access to specialized hardware such as GPUs or SSDs. We could have distributed calculations that we want to spread over hundreds, if not thousands, of virtual machines rather than running just on multi-threaded within a single instance. We want to be able to integrate with the autoscaler. As the number of calculations that we're running inside of our application increase, why not dynamically distribute that over more and more hardware horizontally? And then the final example here is on HPC. High performance compute relies on this idea of doing stuff in parallel, doing stuff over multiple threads, over multiple cores, over multiple virtual machines, and ultimately over multiple data centers and multiple regions within the cloud. And incorporating all of that complexity into our code as developers is not achievable. It's not feasible for 99% of organizations to build that complexity themselves. So we can lean in on some of those capabilities inside the cluster. So we'll come back to a more concrete example of this in just a minute. But there's something else that we need to be aware of inside the API. Because things are happening declaratively and because Kubernetes runs on events, we have this concept of watching the API. So a great example of this is that pod that I just created. I might not want to return success to my user until I know that that pod is running and that it's healthy and that everything looks as it should. Now, without a watch API, I would resort in polling. I would poll that API and say, is it running yet? Is it running yet? Is it running yet? And when it returns and says, yep, I'm running, that's when we return success back to our user. The problem with that is heavy. It uses a lot of HTTP connections, it's memory intensive, and it's complexity that we can do without. So the Kubernetes API has this capability called watch. And the watch API essentially means that I'm going to create a HTTP connection into the API server. I'm going to subscribe to a particular event, and I'm going to wait for that notification back on the HTTP connection to tell me when a certain state has been triggered. So we could say, tell me when that pod is running, or tell me when that calculation has finished the first 3 stages, for example. And there's an example here again in Python. All of our client tools wrap this watch API for us. So on the .NET side, we can create delegates and we can do event-driven callbacks. We don't have to worry about iterating over certain object types. So again, we'll have a look at another example here just to see this in action. I'm going to go ahead and exit that one and just clear this one out here. This code is a little bit verbose, but it's verbose intentionally just so that we can see those concrete steps happening inside the code, inside the application's logic. So the first thing that we're going to do, instead of creating a pod, we're going to create a job. here inside the cluster. So we're going to call this a translation job. And inside this job, we're going to give it the specification for a container to run. And we've got a container image here called the translation engine. And this is essentially a legacy component that as part of a fictional project that we want to bring into the cluster and start executing in parallel. So we can see here, we're just testing this one out. We're going to say, can you translate "hello, my name is Liam" into French for me? Could probably do that one myself with a couple of minutes, but just an example here to help illustrate the concept. And I'm going to dispatch this job into the Kubernetes cluster. And I'm going to rely on the scheduler finding the appropriate hardware to go and run this job and let it run in the background. And when it's finished, render that result back to my user. Now, this is a trivial example doing the translation, but this could be executing a machine learning model. This could be doing some rendering. This could be doing a complex risk simulation. There's lots of scenarios here where, yes.
It's something I used to do quite a lot of work with could do a batch.
Yep.
Not heard it for a long time. Is this sort of the way you would do that today, or would you still go and go batch?
It's the way a lot of people are. Absolutely. That idea of dispatching a batch job into an engine. Yeah. Yeah, absolutely. Some of the advantages that we have here is the scheduler in Kubernetes is much more sophisticated than we have in Azure Batch. So this idea of saying this calculation needs to run on some kind of specialized compute, whereas this part of the calculation can run on commodity hardware. And we have much more sophisticated control over that inside the Kubernetes API.
Yeah, it's sort of behind.
Yeah, exactly that. So we'll jump past that specification a little bit. We can see here on line 36, we're going to talk to the API and we're going to say, hey, go and create this job for me. That's going to happen pretty quickly. That's going to get committed into the state store pretty quickly. And it's going to come back and just confirm the job name that it's been given. We then want to wait for that job to complete. So for that job to complete, a few things has to happen. First of all, the scheduler has to allocate a virtual machine to deploy that workload to. The kubeproxy, or the kubelet on that machine then needs to create the container inside the container runtime. If it's a brand new virtual machine, we need to go and pull that container image down from a registry and run it on that machine. Then we have to run the calculation, or in this case, the translation, and only then will we have the result to send back to our user. So we then have this watch implementation here. So we are subscribing to the job API, and every single time we get an update on that API, we're just going to run some logic here to say, has it succeeded yet? Are we done? And if so, we're then going to break out of that and implicitly dispose of that watch object. Once the job has completed, we can then go back to the API and say, can you tell me the pod that did the calculation for me? So we're going to go and talk to the pod API to go and retrieve the particular pod name that was responsible for doing that calculation. And then finally, we're going to go back to that API, talk to the logging API to say, can you give me the logs from that pod so we can see what happened? So there's quite a few steps there. And hopefully, if I can get the screens right on this here, we should see some of this happening as we run through. So in the terminal at the bottom here, I'm just going to run that program, the create job. In the background, we're going to see that job get created inside the cluster. We can see it's running. It completed pretty quickly. And that watch API has pulled it out. Bonjour, je m'appelle Liam. Some interesting rendering in the console there for an apostrophe. But the translation completed. Once that watch subscription returned, we're then able to return the response back to the user.
So you don't have to compile that code, you're just running it in a...
Yep, I've just ran .NET Run. So I've written the code in VS Code. I'm just using the .NET CLI and SDK to run that. We can have a quick look at what's happening in the background here. So within the Kubernetes cluster, we can see that the translation job was created. That translation job created a pod. We can open this pod up and have a look. We can see that this pod was scheduled onto VMSS 000003, which is the node that this job was dispatched to. And if we jump over here and just have a look at the inputs to this particular calculation, if I can get the zoom right, and it's disappeared because it expired. We'll have a look at it on the next one. So the reason that disappeared then was because Kubernetes is cleaning up after itself. And 60 seconds after the job was completed, it's going to go and delete it. And I talked too long, so it deleted before I got there. So we're starting to build on this scenario. First of all, we have the ability to talk to this API. Then we have the ability to dynamically create applications and components inside the cluster. And then we've got this example of using this watch API where we can both dispatch some work into the cluster, let it happen at whatever scale or whatever cadence we need it to, and then when we're finished, get that response back. So the final thing that we've not talked about yet is in cluster. All of the examples that I've shown you so far, I've been running locally on my laptop here, talking to the API via its public IP address. In this example, we're going to actually deploy the workload into the Kubernetes into the Kubernetes cluster. So inside that data plane that we talked about earlier, I already have a web application deployed up and running called the translation service. This is an ASP.NET Blazor application. It has a text box where we can type in some text and a button that we can press to run translation. So we can send that request into the translation service. We're then going to demonstrate some parallelism. So we're then going to get Kubernetes to translate multiple languages concurrently. So this is an example to kind of demonstrate how we might orchestrate a task over multiple pods across multiple virtual machines. In the illustration here, we've got 3 languages. I think in the demo application, it runs 6. Just to kind of put this into perspective, the project that I was working on this time last year doing a similar model was dispatching 1 million jobs into the cluster concurrently. So using the same APIs, the same programming paradigms that we're seeing here, instead of saying, can you complete 6 languages for me, it's sending 1 million risk simulations into the cluster concurrently and letting the Kubernetes scheduler coordinate and distribute those tasks inside the cluster. The API server is going to receive that request. The scheduler is then going to be responsible for scheduling that work inside the cluster. And it's going to do this by optimizing for 2 things. 1, availability. So we're going to spread across as much hardware as possible. And it's going to do it based on cost. So we're going to increase the density as much as possible. So we're not wasting hardware wherever possible. So those pods are going to spin up. In the demo that we just ran, we saw 1 pod spin up because I only asked for 1 language. We're going to see a pod spin up for each language that I'm going to request. So in this demo, we're going to see 6. And when they're completed, we're then going to send the response back to the UI and render that out for the user. So we'll dive back over. Hopefully, everybody can see this okay. I'm just going to refresh that so we'll make sure it's live. In fact, first, let's go and have a look at some of the code. So we'll jump over here, have a look at our in-cluster web app. And I'm going to jump straight over to the UI here. We don't have to worry too much about this. I'm not a UI developer, nor do I ever want to be. It's not where my professions lie, so please don't judge me on the UI. But we've got a form here where we can submit some text, hit a button, and then we are going to call out to the translation service, and we're going to say translation service.translate, and we're going to give it the input, and we're going to give it a list of languages that we would like it to translate. Now, if we go and have a look at this translation service, if I can remember where I put it, in services here, translation service, and get rid of that on the side, we can see the method that's handling this. And we're essentially just going to iterate over that list of languages. In this case here, the 6 languages that we're inputting. And for each of them, we're going to dispatch a translate job into the cluster. Now, if I jump over to this translate method here, the code that we see is going to be pretty similar to the code that we saw in the previous demo. So for each of these languages, we're first going to create the job. We're going to wait for that job to be complete. Once it's completed, we're going to go and retrieve the pod that did the work, and we're then going to retrieve the output from that particular translation. So code is exactly the same. It's refactored slightly in here, so we split that code over multiple methods, but the code is exactly the same. Let's go and have a look at this running. We'll close that one, and we'll put some text in here. Let's go with hello, my name is Liam. First time I did this demo, I wrote, can you give me directions to the nearest library? Because that's what everybody taught us when we were doing our math, our Spanish and our French at school. And then I realized that nobody goes to libraries anymore. So my name is Liam, how are you today? We're going to translate that. Immediately we see those six jobs have been dispatched on the right-hand side. They won't take long to run. That translation process is pretty quick. Each of them has completed. And on the left-hand side, in parallel, we've got all those results back. Anybody know Japanese? No?
The Spanish looks good.
The Spanish looks good, yeah. We can put it to the test later if you like. I don't know Japanese, but I'm going to trust that that looks okay. But the key thing here is not the stuff that's on the left. It's the piece on the right here. And we can see that kind of parallelism taking place. We've got multiple jobs being dispatched into the cluster. Each of them is associated to a pod, which is that small deployable compute that we have in the cluster. And if I dive into each of these individually, we'll see that they've been evenly spread across the cluster. So if I had 3 virtual machines that made up my cluster, each of them would have received 2 of those jobs. Again, as we scale this up, we're optimizing for those 2 things, that spread and that resource density. But we can go and have a look at one of these. I don't know which language we're going to get here, but we can see again, this one here is being controlled by this particular job. It's being deployed into virtual machine 3. And hopefully if I get there before this one times out, we can see the configuration for that job that's being dispatched into the cluster. And if I come down here, we can see that input. This is the pod that did the Polish translation. Input here, hello, my name is Liam. How are you today? So before I wrap up, I think we've got a minute or 2 that we can take some questions for as well. I want to kind of reiterate that use case because all of the demos that I've done today is not how we would do it in reality, right? If we wanted to do translation, we would go and find a HTTP-based translation service provided by your favorite cloud provider. And we would talk to it by HTTP and it would turn back and give you the result. We wouldn't need to distribute that over multiple pods. But it's a good illustration. And in reality, when we think about gaming studios that are doing rendering across huge amounts of compute, when we're thinking about organizations that are training AI models and machine learning models, they're doing that across a huge amount of compute. When we think about financial service organizations that are running these risk simulations, those calculations are incredibly CPU intensive. It's not possible for us to run it on a single machine, no matter how big that machine is. And it's also not feasible for us to write all of that code in our .NET, Python, or Haskell applications ourselves. So being able to lean in on this technology that is rock solid, it is rock solid production ready for doing this stuff at scale, gives us a real opportunity to kind of deliver the value that we want to build without having to mess around with scheduling and orchestration and all that good stuff. The other really interesting scenario here is where we've got, as an organization, legacy software. We've got stuff that's running on premises today. Maybe we're interfacing with it using a command shell or a terminal, and we want to automate that process. Well, bring that up rather than interfacing with it with a HTTP API. Just ask Kubernetes to go and invoke that software for us and give us the result back. So lots of interesting scenarios. I think we are about on time, so there is a few minutes or so for some questions, if there are any.
There is enough documentation and examples around these days. If we will just ask ChatGPT for, it will write this code for us.
Yep.
Okay.
Yep, absolutely. I will confess, as I built some of these demos, GitHub Copilot was getting in the way and writing half of it for me. So if you want to ask ChatGPT how to write some of this stuff, or get Copilot to do it for you, or go and search out the documentation, there's plenty of samples there. GitHub Copilot, the non-X one.
And the not X one is sometimes struggling with the standard
Yep.
stuff. So.
Yep. What I would say, not that I like to discredit AI and all of the power we have at the moment, but the Kubernetes documentation is fantastic, and we can just go and have a look at it. I'll grab a link for you in a minute. And for every one of those client libraries that I showed you, even the Haskell ones, there are repos on GitHub of samples of how to do it, how to list pods, how to create jobs, how to talk to the Watch API. So if you want to have a look at samples, we don't need AI to write them. We can go and have a look. But I will get a link for you. Any more? If not,